Alright, what's up guys? So today we're going to do the fourth and final installment of our lipids series. So some of you guys might have already seen a lot of this because we covered this in one of the sections before the pandemic hit, but we'll go ahead and cover it again for everybody here. So this is a synthesis reaction that we saw earlier in the semester. So we have a carboxylic acid and we have an alcohol, and we're reacting them under acidic conditions. So what type of molecule are we synthesizing? I want you guys to think about that before you move forward in this lecture. So if you guess that we are synthesizing an ester, you would be correct. So what does this ester look like? So go ahead and pause the video and see if you can draw the resulting ester. Okay, so the resulting ester should look like this. So how do we name this ester? So go ahead and pause the video and see if you can come up with an IUPAC name for our product. If you said methyl propanoate, you would be correct. Okay, so while we're talking about esters, what if we made both reactants really long? So what if we started with a really long fatty acid, so a really long carboxylic acid, and a long chain alcohol? So we're going to do the same reaction. We're going to react them together under acidic conditions, and we're still going to produce an ester, but we're going to produce a very specific type of ester, and that is a wax ester. So waxes are a mixture of water-insoluble esters, alcohols, and alkanes. And each wax ester is going to be composed of a fatty acid residue between 14 and 36 carbons, and an alcohol residue between 16 and 30 carbons. So you guys don't need to memorize those numbers for the exam. Just know that both the alcohol is a long chain and the carboxylic acid is a long chain. So what is the biological purpose of wax esters? So what are they good for? Well, the main thing they're good for is to prevent water from entering or leaving an organism. So here's 3 examples I want you guys to be familiar with. So 1, human skin. Your skin has lots of waxes in it, helps keep them soft and waterproof. Waterfowl feathers prevents waterlogging and allows them to float. And plant leaves, so think about plant leaves, they're going to have a high surface area to volume ratio. So without something to protect it, like these wax esters, you would have significant evaporation and the plant leaves would just shrivel up. So while we're talking about esters, could we form 3 ester linkages on the same molecule? So the same reaction that we've been looking at all semester, where we have a carboxylic acid and an alcohol, carboxylic acid and an alcohol, carboxylic acid and an alcohol. It just so happens that all 3 alcohols are on the same molecule. So when we perform this reaction under acidic conditions, we should be able to get an ester linkage between each carboxylic acid and each alcohol on this glycerol molecule. And if we do that, we're going to produce something that you guys probably have heard of before, and that is a triglyceride. So what is a triglyceride? So a triglyceride is a triester derived from the sugar alcohol glycerol and 3 fatty acids. This is going to be the main constituent of both body fat and vegetable oils, and they usually contain 2 to 3 different fatty acid residues. So what I mean by that is, if we look at this example triglyceride down here, usually you have at least 2 different fatty acids making it up. It's rare to see a triglyceride made up of 3 of the exact same fatty acid residues. So we can classify triglycerides as saturated or unsaturated, similar to how we did fatty acids, but the rules are a little bit different. So it's kind of best 2 out of 3 wins for triglycerides. So if at least 2 fatty acid chains are saturated, then we consider the entire triglyceride to be saturated, even if that 3rd chain has double bonds on it. So the same thing for an unsaturated triglyceride. If at least 2 fatty acid residues are unsaturated, if at least 2 of those fatty acid residues have double bonds on the carbon-carbon chain, then we consider the entire triglyceride to be unsaturated. Okay, so let's talk a little bit about the physical properties of triglycerides. So these are going to follow the same rules as free fatty acids. So I want you to pause the video and think about this first question. So how does increasing the number of carbon atoms affect the melting point? So as we increase the length of the fatty acid chains that make up the triglyceride, we're increasing the surface area between neighboring triglycerides. So if we're increasing the surface area, that means they're going to be able to form more London interactions between the chains. That's more forces that we have to break, meaning we have a higher melting temperature. Okay, so what about saturated versus unsaturated? So go ahead and pause the video and see if you can come up with an explanation for that. So the saturated triglycerides are going to have a higher melting point, right? Because they're going to have more surface area interacting with neighboring triglycerides. So an unsaturated triglyceride is going to have some kinks in the carbon chain, and that's going to decrease the amount of surface area between neighboring triglycerides. So decreased surface area means less London interactions can form, meaning it takes less energy to break them apart. Hence, we have a lower melting point. Okay, so what about the biological roles of triglycerides? So there's three that I want you guys to know for this class. The first one is thermal insulation and buoyancy. So think about blubber in seals, penguins, or other aquatic animals. The protective triglycerides found in the blubber in these animals is one of the reasons they're able to survive in such cold temperatures. So something a little bit more relevant for us is padding. So the adipose tissue that surrounds all of our vital organs is made up of triglycerides. And last, and probably the most delicious role of triglycerides, are energy source. So dietary lipids, which are predominantly made up of triglycerides, contain 9 kilocalories per gram of potential energy. So what about carbohydrates and protein? So dietary carbs and dietary protein. How much potential energy do they contribute when we consume them? So both carbs and protein are going to contribute 4 kilocalories per gram. Okay, one more reaction that you have seen earlier this semester. So what type of reaction is this where we have hydrogen gas being added across double bonds in the presence of a metal catalyst? So go ahead and pause the video and see if you can come up with the name of this reaction. That's right, it is catalytic hydrogenation. So what do we get if the hydrogen gas is the limiting reactant? So in this example right here, we have 4 double bonds that we're reducing. So we have 4 moles of hydrogen gas. So what if we only had 2 moles of hydrogen gas for every 1 mole of triglyceride? We wouldn't be able to reduce all of the double bonds, and we would end up with something called a partially hydrogenated oil. So partial hydrogenation is a commercial process where you take vegetable oil and you treat it with H2 and a metal catalyst. But you're going to halt the reaction before all double bonds are reduced. So this gives you a semi-solid product like margarine or shortening that's good for cooking, but doesn't have the cholesterol levels present in animal fats. So why has this kind of gone out of favor? That sounds like a good thing. Well, it's because the hydrogenation catalyst can convert cis double bonds to trans double bonds. Essentially, that metal catalyst is going to open up the double bond, and if there's no hydrogen gas to add to it, because the hydrogen is the limiting reactant, it's just going to close back up and form another double bond. So when it closes back up, there's a chance it can close back up in the trans conformation, and that's going to give us trans fat. And trans fat is notorious for lowering our HDL levels, changing membrane structure, and increasing the risk of heart disease. Okay, so let's look at one other type of reaction that we have already seen this semester. So what type of reaction is this where we hydrolyze an ester using sodium hydroxide or potassium hydroxide and heat? That's right, this is a saponification reaction. So what if we use a triglyceride instead of the molecule above? What do we get as a product? So when you saponify triglyceride, you get soap. So what is soap from a chemistry standpoint? So soap is a fatty acid salt. So it's going to be the ionic compound that results from an acid-base neutralization reaction. And in this case, our acid-base neutralization reaction was a fatty acid and sodium hydroxide. So these salts are going to be amphipathic compounds that can form micelles. And so that's what's going on in this graphic right here. So imagine this as a shirt that you got some dirt on or some grease, something hydrophobic, and it's not enough for water to be able to wash it away. The water can't interact with it because it's hydrophobic. So what we can do is we can add some soap. So these yellow sections are the carbon tail that is hydrophobic, and the red section is this charged area that's able to interact with the water. So these hydrophobic sections are going to surround the hydrophobic dirt or grease, and the red sections, these hydrophilic sections, are going to be able to interact with the water, and the water is going to carry the dirt away with the soap. So what are the properties of soap? So we can make soap liquid or solid by altering two things. We can alter the cation, or we can alter the saturation. So if we saponify our triglycerides using sodium hydroxide, we're going to end up with a more solid soap. If we saponify our triglycerides with potassium hydroxide, we're going to end up with a more liquid soap. So there's a few reasons why you get a difference in solidity based on which cation you use, but one of the reasons that is within the scope of this class is atomic radius. So I want you to look at your periodic table and tell me which atom is going to be larger, sodium or potassium. Okay, so looking at our dynamic periodic table at ptable.com, we see that sodium has an atomic radius of 190 picometers, and potassium has an atomic radius of 243 picometers. So that means that potassium is going to have this positive charge spread out over a much larger surface area than a sodium ion will. That means it's going to be able to form ion dipole interactions with more water molecules than a sodium ion would be able to. So the more water molecules you can interact with, the more soluble you're going to be. So that means potassium is going to produce a more liquid soap. So what about saturated versus unsaturated? So this one is probably a little easier to predict because it's the same principle we've been talking about with everything else concerning saturation. So the more unsaturated you are, the more kinks you're going to have in the carbon chain, the less surface area you're going to have in contact with neighboring fatty acid salts. So you're going to make less London interactions with the neighboring fatty acid salts. So it's going to take less energy to break you apart, and you're going to produce a more liquid product. So the more saturated, the more solid, the more unsaturated, the more liquid.